We can start. We are live.
Okay, yeah, sure, sir. So, hello and welcome everyone to another lecture as part of Latent Space, which is a new initiative by where we are focusing on young minds who are taking part in artificial intelligence research. And today we are fortunate to have with us one such person, Yatharth Sharma, who is a 17-year-old high school student, and he will be giving us a talk on modeling the human voice inside the architecture of modern speech synthesis. So I will give a brief background about Yatharth. He is an AI researcher specializing in speech synthesis and generative audio. He is the first author of a research paper published at Interspeech, which is a core A rank conference. He developed LuxTTS, which is an open source project which with about 5.3K stars on GitHub, and his models have ranked among the top 25 of over 2 million models on Hugging Face. And his work has also been integrated into major AI projects, including VoiceBox. So I would like to hand over the session to Yatharth to begin his talk.
Thanks, Abigail, for introducing me. Essentially, in this presentation, what I'm gonna go through is like what I learned about how modern speech synthesis models work, and what I learned, and I think what the overall open source and industry also like essentially uses as the architectures. And I'm gonna start from like how we even model speech to like how architectures like in fact generate speech and understand speech and etc. So the first question we should start with is how do we even model audio? So the problem is digital audio often uses a 24 kilohertz sampling rate, which basically means it takes around 24,000 samples of a sound wave just to record 1 second of audio. And the problem here is that this is just too complex. So if we have a text-to-speech model, it would have to predict 24,000 samples to generate just 1 second of speech. And this is going to be really inefficient and very slow. And as well, it would also struggle to learn any relationship since 24,000 samples is a very significant number. So we're gonna in this presentation we're gonna like see how each architecture tries to solve this problem using many things and like how it does it each differently. So the main solution here is audio codecs. We use audio codecs to compress these thousands of raw samples down to a fraction of the size. The architecture depends. Each one can be either quantized into discrete tokens, which basically a specific language model based text to speech model would use, or it can be kept as continuous representations. These can be used for diffusion based text to speech models or any audio model. And the main part here is that these audio codecs turn like this impossible sample level prediction into a much more manageable problem for these audio models. But it is a very lossy compression and it depends on many things. So there are a few things to keep in mind. So in each audio codec, the first probably main important thing to know is the rate or compression rate, as we can see in hertz. So essentially, what this means is, let's say we have 24,000 samples, and what a codec, like for example, a new codec, would compress those 24,000 samples down to just 50 samples, which is a very big compression rate. Uh, Higher usually means a better quality, but that also means the audio model has to generate more tokens, which means it will be slower as well. So it's a trade-off. The next important thing we should note is the number of codebooks, which is basically means like how many token streams. So new codec only has one token stream of 50 rate at a 50 rate, But something like speech tokenizer has 8 separate token streams at 50 hertz. So essentially, more token streams also does more better quality, but at the same time, again, you have to use a more complex architecture to generate speech, and it's usually a bit slower as well. And the last thing is codebook size. Now, this is not as important as the other two, but it's still important to note. It's basically the vocabulary size. So something like new codec, that means there's around 65,000 possible audio tokens. While if you check it, let's say wave tokenizer, there's only 4,096 possible speech tokens. A larger vocab does pack more detail, but actually it's kind of a free trade-off. Usually it doesn't really slow down the model significantly, but it might increase memory a little bit. So it's again important things to note. So the first real architecture we're going to look at is a single codebook language model based audio model. And essentially the architecture is pretty simple but very efficient. So the thing is we use audio input and we use a audio codec encoder, and this is something called usually FSQ based, finite scalar quantization based. So what happens here is, let's say we have like a codec like new codec. It compresses into 50 hertz, and it's just one codebook because of FSQ. And 50 hertz basically means just it has to predict 50 tokens to generate 1 second of audio. And the main thing is it compresses it into audio tokens, and we use a language model to predict these audio tokens or text tokens. And the really interesting part about this architecture is that the language model basically treats speech tokens identical to text tokens. You'll add it to the vocab, and it's going to predict it the same way it would predict text tokens or so. For example, new TTS, it's a simple text-to-speech model trained on using new codec. Lhasa is interesting because it can actually predict audio tokens, but there's also a variant that can predict both audio tokens and text tokens. So you can also do like simple text-based conversation with it while also generating speech with it. And 2cent TTS, another thing is that it's not only limited to text-to-speech, it can also understand speech as well, and it can do also plenty of other tasks. So the main benefits are that first of all, it's a very simple arc, language model based arc. So that means any like library you have, like for example, VLLM, that's a very efficient library to like optimize language models like ChatGPT and Llama but the you can also optimize this architecture and make it really fast for inference. And there's also very efficient training libraries, and it's a very simple architecture. Along with that, it can enable multitasking, like text to speech, speech to text, voice cloning, with just a little bit of extra training. But there are important trade-offs to keep in mind. Since a single codebook carries all audio information, it does require a higher frame rate. So it will be like 50 samples. Some other codecs, if they might have more codebooks, they might be only like 25 hertz. And also the audio quality hinges very much on the codec's robustness. So if it's a poor quality codec, that means the overall audio quality might be poor as well. So that's important to keep in mind. So we want a high quality codec. The next architecture we're going to look at is the multi-codebook LLM-based audio model. And this is a bit different. It uses a RVQ-based audio codec, which basically means it will have multiple codecs. And usually the first codebook means coarse, which means it will contain like the semantic meaning, like what's actually being spoken in the audio, versus the next iterating codebooks might be more the fine detail. So how for example, background information or acoustic information. And in this architecture, it's essentially we have RVQ-based codec. It uses audio input, and you can also input text input. And this usually there's a large language model. It predicts the first codebook, which is the semantic codebook again. And then there's a very small decoder model. The architecture varies for the decoder model. Each one usually uses a different architecture, but it predicts the rest of the codebooks, the acoustic info. And basically, you take both of these generated tokens, put it back into the codec, and you get audio as output. And again, each model does do it a bit differently, but they follow the same main architecture. For example, Quant3 TTS, it uses the decoder model is more of a multi-token prediction model, and for CZM, it's in fact just a smaller language model. So there are differences. So the main benefits are that it allows for a much lower frame rate. For example, we have Mimi. It's a codec, and its frame rate is only 12.5 sampled, so it compresses much more. It does have 16 codebooks, and the model's quality and speed often depends on the LLM more than the codec, which means you can optimize this part. And codec won't like really lower the audio quality, even if it's like not as great as it can. So the trade-offs, again, more trade-offs. Basically, this parallel token stream, it requires a complex setup and complex architecture, which also means you can't often optimize it as easily as the previous architecture. And again, more memory overhead since you need a transformer-based LLM and a decoder model. And in theory, it might like look faster, but practically many RVQ-based TTS models are slower. For example, Quant3 TTS, that's even though they're like similar size to new TTS, it's actually a bit slower than new TTS. And essentially, same with CZM and Qta TTS. So there are important trade-offs to keep in mind. The next architecture we're going to look at is the continuous or diffusion-based audio models. And this one is a bit different from the other two. It doesn't really use language models. And essentially, the audio is compressed into a continuous feature representation instead of like discrete tokens. And usually also for the text tokens, while language model, you can input it directly. You usually need a separate text encoder for these diffusion-based audio models. And then we have a diffusion or flow matching transformer or unit usually. And what this does is basically parallelly like uh, generates the audio, but it iterates. So main benefit of this is basically, first of all, we don't need discrete tokens, which means the compression is much less lossy. In fact, sometimes you do not even need to train the audio encoder. You can use something called mill compression. And then also training is often very stable, and single batch generation can be very fast when distilled to just a few steps. Although usually they start off with around 20 to 50 steps, and then you can distill them to just a few steps. So the trade-offs are that iterating sampling scales poorly across large batch sizes during inference, and because they don't use discrete tokens, they can't easily use any pre-trained text language models for initialization. And also, it's pretty hard to multitask. Well, the previous language models can usually do speech to text and voice cloning. You usually need to adapt the architecture to support those tasks. And the examples are F5TTS, Echo TTS. Echo TTS, for example, uses DocWay, which has a rate of 86 hertz at 9 codebooks. As you can see, this is much more less compressive than the previous codecs, but diffusion flow matching also are more efficient usually, and they can generate large parts quicker. But again, they scale poorly across large batch sizes. And then we have the hybrid audio models. So essentially, hybrid audio models, they kind of try to use the best parts of both diffusion language model and language model and a large language model based architecture. So essentially, we use a audio codec, and this codec is usually much more lenient. And what happens is, so the language model, it usually predicts the high level text content and the sequence planning instead of generating all the fine tokens. And then we use another flow matching decoder to decode these hidden states and these only more the coarse tokens. And then we pass it to the real audio codec decoder. And essentially, the main benefit is that it offloads any fine acoustic information from the language model to the flow matching decoder. And this allows for very low codec frame rates, like only like 7 hertz, which is a very significant compression. For example, 24, it starts with 24,000 samples and now goes back to just 7 samples almost. And it also retains any the pre-trained language model intelligence and long context handling, and it usually achieves very high audio quality and less tokens for the LLM language model to generate. But again, more trade-offs. Inference both requires one like transformer pass and then the flow matching decoder pass, and this means it will be a complex setup and not as efficient as the other ones. And also the latency will be quite high. Language model latencies are usually very low, while diffusion-based model latencies are high, but this one is kind of in the middle as it uses both of the architectures. And as we can see, Vibe Voice, Omni Voice, Cozy Voice 3, these are also very high quality audio models, which so it does prove that the architecture is pretty high quality, but as it is not as efficient as the other ones. Example is the Vibe Voice Way, uh, 7 hertz, and it uses 124 dim. Let me go back. It uses 1024 dim, which means basically a hidden state, and the flow matching decoder decodes these hidden states for the real audio codec decoder, which is usually like a vocoder. And the last thing we have is a duplex audio model. The thing with this is it functions quite different from the other previous ones. It's usually most similar to the RVQ based language model, audio model, but it's basically designed for real time directional interaction. So basically, you can speak, and it can actually process its own speech and your user's speech at the same time. For example, Mosi. Mosi is probably the most prominent example here. Uh, it's very similar to RVQ-based LLM arc, where a primary transform. So you usually have RVQ-based codec, a main transformer. It predicts the first. It predicts a text token first, and then it predicts a codebook 0 token, which is used again semantic token, which again means basically the what the audio is actually saying. And then there's a very small depth transformer. This takes the text token and the codebook 0 token, and it predicts the rest of the acoustic tokens auto-regressively. And then everything is gone back to the RVQ based codec. And it does this for each frame. So essentially, it's actually real time. It gets a user audio, context generated audio tokens again, each frame like 80 each frame is around 80 milliseconds, and it does this continuously. And essentially, what Mosi and Personalplex and the other models can do is that they can, for example, listen to you. They can say mm-hmm or like other audio while listening to you as well, and at the same time thinking using their text tokens. So the main benefits are that it enables any full duplex conversation with sub 200 millisecond latency. Model can hear, speak, and interrupt simultaneously without waiting for a full turn to complete or relying on separate pipelines. But there are trade-offs again. It is a very complex streaming architecture. These models also consume a very significant compute, and it's very hard to optimize as well. And they often suffer for training or generation instability, and the audio quality can be poor if the training data is poor. A very important thing to note is that training these models are usually pretty hard because you need lots of duplex audio data, and relative to text to speech or speech to text, you have many data sets for text to speech, but duplex audio is a bit more scarce and is not as much. So you usually have to find lots of data and train as well using very separate losses and much more. So that's around it. I think. hmm, Yes, I think that's about it.
Okay, thanks Yatharth for that talk. And let me quickly check if we have some questions coming up. Uh, Hold on. Meanwhile, could you share like a bit about your the kind of research the you already have published, right? So at quite a young age. So if you could share a bit about, I'm sure there must be some questions coming up around that, like other students watching of your age generally. People enter this domain much later in when they're in undergraduate, right? They get the exposure
Yeah,
to
I
research.
think
Your voice is breaking.
All
So good.
right, so okay, you can do it. So I should tell about my paper. Yeah, sure, I'd be happy to. Essentially, it was based on a fast and flexible audio bandwidth extension. So the main problem I was trying to handle is that, wait, let me go to presentation. Many of these codecs and text-to-speech models, they're limited to usually 24 kilohertz sampling rate, which is not bad, but that means it can only represent frequencies up to 12 kilohertz. And while humans can usually listen to like 24 kilohertz, so basically it loses lots of like clarity and like the crisp audio. So basically, my research paper was on developing an bandwidth extension model. So basically, it enhanced the clarity and the audio quality of any of these text-to-speech models or codecs. And the main novel part was that it used a optimized architecture, a Vocos-based architecture. And so previous bandwidth extension models, they were usually like very slow diffusion models. In fact, sometimes they were even slower than the text-to-speech model itself. So my paper was on developing an efficient one. It was called Lava SR, and essentially it basically was much faster. It was up to like 10,000 real time on a GPU. That means you can
Mhm.
like restore any poor audio quality like very quickly. Like I believe you can restore an hour of audio quality in just 3 or 4 seconds.
Wow.
Uh, Yeah, and basically for any like text to speech, or any like speech, basically any speech thing related, and it
Mhm.
was very efficient to train and inference.
Well, that's great, and I think we'll probably share some links in our YouTube description, regarding your research, so that people can take a look further into it if they wish. But I was also asking, like, the further follow up question on that, like, how did you get introduced? I don't believe you have mentioned that, like, during this talk. Like, how did you get introduced, to this domain and getting so hands on and publishing? Do you, yeah, if you could just throw some light on that.
Yeah, sure. Essentially, I think when I first saw ChatGPT, I was really interested by AI. And then essentially I started looking at open source things. I was still a very beginner, but I started looking at open source things, trying to use any like open source model, like text to speech model and language model. And eventually I really liked audio models because I could tinker with them, and they didn't require like huge significant amounts of memory or resources, while like relative language models, they require like very significant resources. Even
Right.
image or video models, they've only become really like popular nowadays, and they were also very heavy. And audio models, I could actually like tinker with them, train them, experiment with them. So eventually, I started going in like audio communities.
Mm-hmm. Okay. Oh, I think your voice is. We just lost you. I thought.
Uh,
Yeah.
is
Yeah, now it is fine.
Yeah.
okay. Yeah, so I was just starting. Basically, yeah, so I started tinkering with audio models. I went to a few audio communities like in Discord and Reddit, and
Oh.
eventually uh, thought of like actually open sourcing my first repository, and I did. I got a few stars here and there, so I thought, why not go a bit further? And then I started more open sourcing more things. Eventually, after much repos, I got a 5,000 star repository, and I started also publishing a paper based on other papers I read. And I think basically I was just interested in audio modeling, since it's a very like if it like a domain where I could like do a hands-on research and like actually tinker while on my own home GPU, instead of like using tons of resources essentially.
Yeah. Yeah. That's a very good point. I think because that is a big hurdle otherwise for people who are initially trying to get into training these large models. So great
Yeah.
insight, and that will help a lot of young viewers who are watching. I think Shishir sir has a
Yeah.
question. Yeah, he wants to ask.
Hi, Yatharth. So it's very interesting the way you present it, and you cover like the whole pipeline and the whole history of TTS. Recent TTS development at least. Hello, am I audible?
Yes, yes.
Yeah.
Okay, okay. So one thing I'd like to know. There will be like few questions from from student perspective, right? Because as Vigan mentioned, you did something like that kind of work actually people generally do during the undergrad or maybe PhD or something. Okay, so I'll ask maybe questions from that point of view, from student point of view, and a research point of view actually. So, when you developed this last LuxTTS, you told like you did based on that Lava one you mentioned in that. Now, for example, currently those models are in for English language, right?
Yes, most
Yeah.
of them.
So, for example, like if we want to do for other languages or maybe some low resource languages, so what will be the way, and what is your plan? Are you planning to are you planning to open source the code base and model weights? What is your plan actually going forward regarding your LuxTTS?
I think I think training pipelines are the most useful. And I think the hardest thing is usually the audio data. You need like usually like several hundred hours of audio data at the least. So very like niche languages or any specific languages, it does get a bit hard. And you usually need very high quality data to make the text to speech model actually like good quality. So I think the most important part is to get audio data, and I think any training pipeline you usually want to look at an open source model which has their like training pipeline open source, because if they don't, then it's usually like very difficult to train yourself. And if you do, it's usually you forget, like they usually have very internal things you need to be careful of, and it's kind of very like faulty. So I think, for example, I was experimenting with a new TTS model that has a good training pipeline, and you can train from multiple languages. It's Orpheus also. It's very efficient to train from multiple languages. And I think you can often just train on a free Kaggle instance sometimes if you don't want to spend like hundreds of dollars. It will take some time, but I think you can probably train on a Kaggle or Colab instance. And I think basically uh, I think data is the most important part for usually languages, other languages than English.
Okay, okay. So for regarding because your paper is not yet I mean open. I think once that interspeech will over, then we can see that we can read the paper in ISCA archive. Uh, so can you give some idea like when you train that LuxTTS, like how many hours of data you used for our users, for our audience, like how many hours of audio you use for training the model, then maybe like what is the number of parameters, if it is possible to share those information actually, and then how many
Yeah,
GPUs you use, yeah. So,
yeah, sure. Basically, for LuxTTS, I use the Libri TTS dataset. I forgot how many hours. I can actually search it right now. Let's see. Yes, around I believe 600 hours of audio. And also, I believe I used my own GPUs and rented out a few GPUs from a model. They also give free credits for like high instances, like A100 or so. So you can use that possibly. And the parameters, LuxTTS is only, I believe, like 120 million parameters. Let's see. Yes, I think it's only, let's see. Yeah, it's essentially around 120 million parameters, which means it can fit in around 1 GB RAM or so.
yeah, right.
And
So
actually,
it's very
yeah,
small model actually.
yeah, yeah.
Okay, okay. Just wait. So uh, next question, like we got one question. I'll just read it out. Uh, so here, for example, when you build this TTS, like as you mentioned, like your TTS have been using uh, by different person or different in the organizations. So what I mean, when you develop this TTS, because now most of the TTS is like this audio tokens, then how to compress, then backend there will be LLM, all those things stuffs will be there. Okay. Now, what are the things? For example, there will be like naturalness, expressiveness, latency, computational cost. So, how actually manage to what to compromise and what to not? So can you give some idea on that actually? For those developers like who wants to start building their TTS, own TTS?
Yeah, sure. So I think the main part is, first of all, you have to like compromise. Like, do you want efficiency? Like, you want to run it on very low end devices, or are you gonna be like serving it on high end devices, like with like a 800 with like 40 GB RAM, or are you gonna like serve it on like an iPhone or so? If you're gonna serve it on an iPhone, then I think probably you might actually use some continuous based audio model, because they're very, if you distill them to like just a few steps, they can be very fast on just in just like 1 or 2 steps. They can probably generate real time on even on an iPhone. if you can optimize and distill them. And let's see, if you want to like you actually like you want to use it in like industry or scale it, then I think let's see. Then I think probably a multi-codebook LLM-based audio model is the best, like QuantiTTS. This is from a very big company, like Alibaba, right? So if you want to like serve it to very much users, then like QuantiTTS. If you want to like just run it on an iPhone or so, or like like on a phone or like a local device, then maybe a diffusion-based audio model or a single codebook language model. Essentially pretty much that. And again, if you want to really start from scratch, then I think the most codecs to optimize is probably either new codec or doc for like diffusion. I think you basically pretty much that.
Okay, okay, interesting. So maybe like developing new codec also like may be important for the use case. It depends on the use case because
Yeah.
how much you want to compress and all. So this LuxTTS is streaming one or
LuxTTS is not streaming. It actually
not streaming? Okay.
uses this diffusion based audio. This part.
Okay, diffusion based model. Okay.
Yeah.
Um, so, I mean, what do you think? Like currently, because we are developing voice agents and all. So, in that scenarios, like people are developing that kind of applications where we need interruptions, and then it should be done within maybe 500 or less than 500 millisecond to so that like conversations feel very natural. uh, so, what kind of TTS you feel like it's good for the real voices and applications? So I know like if we have good GPUs and high computing power, then like maybe some good TTS which we can deploy there. But I'm just telling in general. I mean, if I have a consumer GPU and I want to develop that kind of voice agents, uh, for some small applications maybe. So what do you suggest for TTS point of view? I'm asking actually.
I think definitely then any of the language model based architecture is the best one because they have very low latency. Now you need to make sure that your codec is also streamable. Like some of them are not streamable, but I believe, for example, Qt TTS, this is actually very efficient, and this has like less than 500 ms latency. I think it well it depends, but I think it can be around like 200 ms on the consumer GPU. And also new TTS and losses. Some of them are streamable, and 2 cent TTS. If they are streamable, it can usually again be like only 100 ms latency or 200 ms latency. It depends on the device again. If it's a very old device, it might be higher. But if it's like a let's say a 3060 or like a consumer GPU device, then it can be definitely very low latency. But basically, the main thing is use the language model-based architecture. Diffusion is not too good for streaming.
Okay, okay, got it. So it's very nice actually. Um, now you conclude. I mean, your last slide was I think regarding the full duplex speech system. So that is I think one of the hot topic nowadays. So, what is your take on that? And like, I mean, I feel like this is your future, research and making your TTS and integrating it the full duplex system where you can seamlessly you can speak and then you can interrupt and all. Can you give some, I mean, overview on that? What is your next plan on that?
Yeah, sure. Duplex-based models. Let me just go to the slide. They are kind of they are still like in the very early phase. Right now, I think cascaded like a speech to text model, a language model, and a text to speech model is much more stable. Because the problem with like duplex audio models right now, like MOSI, is they're like somewhat unstable and they also don't have much customization. But I think there's lots of research going to like make them much more stable, to do tool calling and like voice cloning, and much more. Because duplex models, in theory, they're very fast and they can hear, speak, interrupt you, and everything. But at the same time, they are very unstable and uncustomizable. So I think right now most of the industry still uses cascaded audio models just because they're much more efficient, cheaper, and stable. But I think there's lots of research going on that way. I think Personaplex, for example, made mostly much more realistic. LFM audio made it much more efficient, and I think essentially pretty much that. Yeah.
Okay, okay. Actually, I think this interpretable and diagnose. I mean, we can do diagnosis like each and every module. So that was the comment for the this before end-to-end system, even for the ASR and all. But now eventually, like ASR become end-to-end, then TTS become end-to-end. So I think eventually this whole pipeline will be end-to-end. Like it will be like full duplex after a few years, maybe. So
Yeah.
okay, great. Yeah. Uh, One last technical question I'll just ask you. Do you think like the future of speech generation will, will remain token based, or you mentioned also like will it be like continuous representations, or eventually like make the discrete token unnecessary? Like what do you think here?
I think most likely the architecture will change a lot because different companies want to be different best at each architecture. But I think diffusion based audio models, they're very good for local serving. They're very efficient. And while I think for language model, I think single codebook is the most simplest because the main part is that you make the model, and then so many people other are maintaining the libraries already, and you get the fastest parts of language models. So VLM can easily optimize your language model, and if you want to do very fast training, you can use a library like Unslot. So either probably this for maybe industry use case, or this for local use case. I think those two are the best. But multi-codebook is also very popular. Like very big companies are releasing multi-codebook ones because I think they are also very efficient for them. But I think the future will change a lot because each company will find something better and try to improve on each architecture. But I think personally, I think the most two best ones are single codebook LLM-based audio model and continuous and diffusion-based audio model.
Okay, 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 understand. If I, for example, you have LuxTTS, right? If I give you maybe some 10 hours of audio of one very low resource language, so how quickly you can adapt to this particular language?
How many hours did you say?
Or maybe 10 hours of data we have.
10 hours. I think I'm not sure if LuxTTS might be able to learn that. I think some other smaller models might be able to at least start getting the language. They might not be excellent with it, but I think that might definitely start learning the language at least and actually speaking it. But I think for high quality you might need more hours definitely. For high quality you might need 100 hours or more.
Okay, okay, great, great. Vigyan, do you have any questions to ask? Or
I think, sir, you have covered all the technical questions.
yeah,
Maybe I'll just ask. Yatharth already mentioned, but this will be relevant for the again young audience watching latent space. So, if you could just, give few closing comments, Yatharth, since you already brilliantly explained. Clearly, you have so much depth on, in these audio models, text to speech models, and could you just, recommend to your fellow high school students or undergrad students who want to move into some maybe speech or some other domain in AI, how can they start building and researching them? Could you give them a few concrete steps that they can take?
Yes, sir. I think open sourcing is a very nice way to learn. You learn yourself. and then you also help the community. The community gives you feedback, and you also get interest, and you learn you learn a lots of things as well. I think like most of this I learned from open sourcing things basically. I learned like actually probably all of this from open sourcing things. And I think once you open source things, basically what happens is that many people, many experts even actually see your work, and then they can give you a review and they can feedback, and then you can also at the same time like uh, do more work, do more open source work. I think also if you want to try out like running a model or doing tinkering, I think any of the Kaggle or Colab, those Jupyter notebook instances, they're very useful, at least for me. And they give you like GPU resources, decent GPU resources for like completely free. And I think probably yeah, speech is a very good idea to work in since it's lightweight. I think images also decent language models. I think actually if you like specialize in a certain field, lightweight field, you can probably do good impact on any field most of the times. And I think that's pretty much it. Basically, open source is very useful.
Great, great. So in open source, you suggested GitHub, and you're suggesting Kaggle and all these for compute, plus Hugging Face. But I recall you're also mentioning GitHub, sorry, the Discord and Reddit, which is quite interesting. We generally don't associate maybe these places with research, or at least I didn't think so. Have you got some good help, or a active research community there as well in Discord, Reddit, these sites?
Yeah, I think so. More so, I think Discord is actually surprisingly a significant amount of researchers there. Like I found significant amount of researchers and engineers and developers. There was a few channels here and there. If you like go to TTS channels, I actually found a lot of support from there, and actually like several researchers as well.
Great, great. I think that is
I
very insightful.
yeah,
Yeah.
we can. I'll just ask one question. Uh, Yatharth, like, can you remember your like early days of, studying speech, and when you first start the speech? Because I feel like it is a very long. You spend a few years spending time to understand audio, then deep learning, then end of the day, like you develop LuxTTS. So, when did you start actually? Like at which class, for example, if I say specifically, start learning all those?
I think probably it's been for speech specifically. I think probably like 2 years, maybe 2.5 years. I think the best way to learn is probably like you can ask people. You can also actually just use. You can also use AI if you want to help. And you can. I think reading code is also very useful, and like writing code yourself. That's gonna like teach you a lot, and you can ask AI to break down papers or code, and then write it code yourself. It's like it is difficult the first times. Uh, I actually started open sourcing maybe only a year ago, but I started learning like 2.5 years ago. So yeah, it does take some time though.
Right, right, yeah. Okay, so yeah, it is interesting actually, because we should start and then build something, then we should open source, then interact with people, and then learn from them. So that's the main path to excel, I think. Okay, so Vigyan, I think let me
Yeah.
check
Like,
once. We
sure.
have any? 1 second.
Yeah.
Okay, so we don't have any questions.
Okay.
Let me.
We are on time also, sir.
Yeah,
Right on
around
time.
time also.
So
Okay,
probably we can close out the session
I
at
think
the,
I think we can
yeah.
close the
Right.
session. Yeah. So Yeah, Avigyan.
Yeah, so I mean, thank you first of all, Yatharth, for this really like inspiring talk. I think all the listeners, and I hope a lot of young listeners who will listen to this, will gain a lot of inspiration and probably start, contributing to this field as well. So thank you all for watching this session, and we hope to see you in the next lecture of Latent Space from I. And thanks again, Yatharth, for this wonderful talk. Thank you.
Thank you,
Yeah,
everyone.
thank
Thank you,
you,
everyone.
thank you, Yatharth. Thank you. So here, like latent space means like we want to explore more ideas like what young people is doing, um, and exploring and contributing to open source. Okay, so I'll stop my this one live.
Yeah. Yatharth, you can stick for like couple of minutes.
Yeah,
Yes,
yeah.
sir.
Yeah.
I stopped.